and for participating in this SAE Smart Track UK network. My name is Ricardo Takahira. I will be the moderator of this event. Okay. First of all, I would like to thank the event's exclusive sponsor, the British government in Brazil and the UK Departments for International Trade, DAT. Before we start, some important information. We kindly ask you, all the participants, to keep your camera and microphone off during the entire event. You can send questions to the speakers on the chat. We will select some of them to ask at the end of each panel during the Q&A session. Please note this event is being recorded and will be available at SA Brazil YouTube channel next week. So this event has the main goal to integrate the main specialists from Brazil and from UK. And I'm glad to hold and I'm honored to host this event. Okay, so first of all, we will have Mr. Lucas Brown, the British Consul from the Belo Horizonte. So welcome, Mr. Brown. Mr. Brown, can you present yourself, please?
Hi, Ricardo. Can you hear me?
Yes, sir.
Thank you very much then. So good morning to those in Brazil. It's just gone noon, so good afternoon, to those joining us from the UK. My name is Lucas Brown. I am the British Consul in Belo Horizonte in the state of Minas Gerais, Brazil. It's an absolute pleasure to be making the opening remarks for this fantastic panel on opportunities in batteries. Just like my colleague, Beatriz Ozaki, who leads the advanced engineering sector for the British government in Brazil, I joined the consulate after many years working in the automotive sector. So it's an honor to support the development of even more business between the UK and Brazil on the future solutions for the sector. There are too many to thank individually, but I would like to give a special thanks to SAE Brazil, with whom Beatriz is developing a brilliant collaboration with. The future of mobility and clean growth are two of the 4 pillars within the UK industrial strategy to put the UK at the forefront of the industries of the future to improve people's lives and the country's productivity. The UK has a world-leading automotive innovation ecosystem with expertise in zero-carbon powertrains, batteries, motors, and power electronics, backed by substantial government R&D funding. This, combined with one of Europe's most competitive car-making industries, offers a UK a huge opportunity. The UK also has 4 of the top 10 research universities in the world, and one of those 4, Oxford University, invented the modern lithium-ion battery in the 1980s, which then led to a UK researcher being awarded a Nobel Prize in 2019. Today, the UK is still at the forefront of battery research, thanks to the world-leading Faraday Institution, which is dedicated to developing new solutions for electric vehicle batteries, which our R&D specialist, Jay Nagley, will go into more detail after me. The road transport sector is a major contributor to greenhouse gas emissions in the UK and worldwide. The UK's government's commitment to the end of new petrol and diesel cars by 2030, and for new cars and vans to be zero emission at the tailpipe by 2035, will play a major role in helping to meet the net zero goal. We don't want to meet the 2030 and 2035 deadlines through importing cars and vans. So securing a comprehensive UK EV industry, both completed vehicles and supply chain, is vital. And this will depend on foreign direct investment, as well as growing exports to build resilience and competitiveness among UK manufacturers. The DIT and the British government aims to strengthen the partnerships between the UK and Brazilian institutions and companies to develop the low carbon technologies that will pave the way in the near future. I hope you enjoy this event and have a great discussion with the impressive lineup of specialists who have been invited to speak. Thank you and obrigado. Ricardo, back to you.
Thank you, Mr. Brown. Now, I would like to invite Mr. Jay Negri, the IT R&D specialist, automotive sector, to talk about the opportunities for cooperation in EV batteries. Welcome, Mr. Negri.
Thank you very much for inviting me, and thanks to Lucas for setting the scene there. So what I'd like to do is take you through a brief presentation setting the scene regarding UK technology capability before you hear from the individual companies who can really deliver that technology. As you've heard, we have a very aggressive policy towards phasing out internal combustion engines. So by 2030, from 2030 onwards, there'll be no pure internal combustion engine cars or vans, and from 2035 they will all have to be fully zero emission. The government's also releasing considerable funds to help develop the technology to make that happen, and that's what we'll be looking at today. So as a bit of background, the UK has a very strong chemical industry, including a strong presence from Brazil in the form of Vale. And that chemical industry gives us a very strong background to develop and manufacture batteries. There you go. So the UK has established a series of targets, and these have been established by the car industry itself, rather than the government dictating what the target should be. The government asked the Automotive Council to come up with what seem like realistic targets to aim for. Most of them are, as you would expect, steadily improving the performance, reducing the cost of batteries, but one that is very important and really hasn't yet come to public attention is recycling batteries. The UK is determined to pioneer technology to do that, because at the moment recycling batteries is very difficult, and we are storing up another environmental problem if we solve the CO2 problem by building batteries that then have to be shredded or put into landfill. That's just not acceptable, especially given the constituent parts of a battery. So we are aiming for virtually full recyclability by 2035. Excuse me. Now, Lucas mentioned the Faraday battery challenge and the work that's going on in the UK to develop new batteries, given our historical strength in research and development in this area. So the Faraday challenge is split into three parts: fundamental research, which the UK is second to none in, given, as you heard, we have 4 of the top 10 research universities in the world. We also have collaborative R&D to take the ideas from the institution towards production. And we have the Battery Industrialization Centre, which is a unique facility, which I'll explain more in a moment. So the concept of Faraday is that it can take ideas from the concept through the prototype to manufacturing readiness, which is a unique ecosystem that no other country can demonstrate at this scale. So the Battery Industrialization Centre is opening right now in Coventry. The first projects are just starting there. And the idea is that any company in the world can come along and develop new technology, either for battery chemistry, cell manufacture, pack assembly, whatever stage of the battery supply chain a company is working in. BIC, the Battery Industrialization Centre, has the machinery and the facilities to develop prototypes in that area. So the idea is that as an open access facility, companies can come along, test their ideas, get them through to production readiness without having to invest in expensive capital equipment of their own, because it's all at BIC, and then they can put it into production. So it's a way of of really removing barriers to get good ideas and good concepts through to production as quickly as possible. And the BIC, excuse me, the BIC is there for the benefit of industry. So we don't assert any rights to IP. Whatever's invented there, developed there, is owned by whoever did the development. It really is there to facilitate the industry. Now, as you'll hear more of today, the UK has companies at the forefront of all the major new battery chemistries and battery technologies. And that gives us a great ecosystem which companies from Brazil can plug into, as what we have organizations at every size and every stage. So relatively small companies developing new battery technology, large companies developing new battery technology, plus the whole R&D ecosystem and the facilities we have to help. And also, I should say that the UK is internationally rated extremely highly in terms of industry academic collaboration. Only the United States scores higher. We're ahead of all other European countries. So our academic institutions and our research organizations are much more focused on getting solutions into a factory than most such institutions around the world. So in summary, we have a huge number of specialist automotive engineering companies, and that really comes out of the historic position we've had as having the world's largest motorsport industry. As you know, the United Kingdom has dominated Formula One for over 60 years now, and that industry has spawned a huge number of small companies with very clever technology, typically maybe 50 to 100 engineering staff who are used to solving very complicated problems very quickly, because that's what Formula One and other motorsport series like Formula E are all about. And they've taken that can-do attitude and that spirit of looking for radical new solutions, and they are selling more and more into global tier ones and global car manufacturers. Global car manufacturers have never done more R&D in the UK than they are doing now, even if a lot of what they're doing is effectively being subcontracted to specialist UK companies who can deliver much more quickly and, to be honest, at much lower cost, because they don't have the overhead structures, they don't have the layers of management. So increasingly, big OEMs are coming to the UK and giving major projects to UK companies, even though the resulting car may carry a badge from a completely different country. And that breadth and depth of engineering capability means that we have the powertrain solutions really wherever the company is looking, whether it's battery chemistries, whether it's electric motors, whether it's power electronics. The UK has a big network of specialist companies who can help, and that really applies at every size, whether it's a small electric scooter that people are looking for, or electrifying a complete global platform for a car manufacturer. So with that, I'll come to an end and hand over to the real specialists who can actually deliver all this technology for you.
Thank you, Mr. Negi. Now we will start the first panel. The first presentation will be lithium sulfur LIS battery technology from Mr. Enzo Pasquale, General Manager, Latin America. Mr. Pasquale, please.
Yes, good morning and good afternoon, everybody. Just sharing my screen. Can you see my presentation?
Not yet.
Well, it's a pleasure to be here today and talk about Oxys Energy and its innovative lithium sulfur battery technology. Oxys Energy is a world-leading research and technology company producing next-generation high-energy density lithium sulfur powered shell for battery system. As you can see here, it's our ultralight lithium sulfur pouch cell, and it has extremely high.
Your screen is not being shared. Could you please
It's
check?
not shared. Okay.
Not yet.
Just a moment, please. Yes, funny enough, it seems it's not showing my screen.
Yeah, Ivan can maybe help you. Right.
Okay, I think that is sharing.
No, now it's okay. Go ahead, please.
Very good. I was saying that our cells have extremely high energy density. We have already tested 470 watt-hours per kilo, and we will achieve 500 watt-hours per kilo in the next months. And with future development of our technology, we are targeting more than 600 watt-hour per kilo by 2025. Oxys has a strong patent portfolio, more than 300 patents, 211 already granted, 102 pending, into 43 families. And Oxys is now at a transitional stage from R&D to mass production of our cells, and this will be in our plant here in Brazil. Now at Oxys UK, we are engaged in research and development of the pouch cell designs and new material development, cell testing, and also we already have a production of cells for testing, for prototypes and development of new application, and also we are manufacturing the components of our cells, the cathode, anode, and electrolyte. And also a battery system. We are developing our battery system pack design. We are building batteries and also developing battery management system designs, system BMS. And our plant in Brazil will produce the cells, but we have all the skills and all the technology to develop a battery system together with our customers. In 2023, Oxys Energy will start the operation here in Brazil of the first lithium sulfur cell plant of the world. So not just in Brazil, but of the world, in the city of Juiz de Fora, state of Minas Gerais. This is a partnership with CODMG, which is the company for the development of Minas Gerais state. The plant is located at the Mercedes-Benz Industrial Park, and will produce more than 7 million cells per year. And it will be to supply to Brazilian customers and also to global markets, and creating hundreds of highly skilled jobs. We can see here is the plant, the Oxys plant. We are currently developing the engineering design for the building upgrade in order to receive our equipment, our production lines. And in parallel, we are also investing in a plant in the UK to produce and supply cathode and electrolyte, which are essential for our cell production here in Brazil. Talking a little about competitive advantages of our technology is, of course, the high gravimetric energy density. I've already said 407 watt-hour per kilo, which is twice the energy density of lithium-ion technology, as we can see here. NMC, we can say about 240 watt-hours per kilo. And if we consider LFP, more or less 140 watt-hour per kilo. So it is more than 3 times its energy density. And if we think of future development, next generation of lithium-ion technology, maybe we can say that by 2025 can achieve 350 watt-hour per kilo. But at that time, we will have reached more than 600 watt-hour per kilo. And I think it's important to have a look at the theoretical gravimetric energy between lithium ion and lithium sulfur. It is about 5 times. So 200 watt-hour per kilo against 580 or something like this. So this is important to understand what the possible future development and improvement of our technology, even higher than 600 watt-hour per kilo. And then together with the high gravimetric energy density concept, there is the battery weight reduction. Our batteries are at least 50% lighter than lithium-ion battery, and in the case of LFP, will be much more than just 50% reduction. Our technology is effectively environmentally friendly because our cells, there is no heavy metal like nickel or cobalt or toxic materials in the composition of our cells. We can see a cell here, the description of the cell. The cathode is composed by sulfur and carbon and a binder. The anode is lithium metal. In between we have an electrolyte, an organic electrolyte and non-flammable electrolyte and a separator. No other elements, no other components. And important also to say that we need, for a given level of energy of battery capacity, we demand less quantity of raw material. So this is also a very good important impact on the environment. And then superior safety performance, as our cells do not explode and do not cause fires. We know what has already happened with the fires in the Tesla cars and explosion with Samsung cell phone, mobile phone, fires in Boeing 787 aircraft. And this definitely is not going to happen with our technology. As our cell can withstand extreme abuse situations, such as bullet and nail penetration and short circuits, and with no adverse reaction, with no explosion. And these are our main applications where high energy density, low battery price, and safety are very important. In the automotive application are for buses and trucks and light commercial vehicles. So reducing the weight of the battery is possible to increase the payload and the number of passengers, of course, in a bus. And choosing keeping the weight of the battery, it's possible then to increase a lot the drive range, which is very important. And in the case of maritime application, we have boats and yachts, and the safety issue is very important for this kind of application, because when you are in the ocean, you cannot, it's very dangerous to have a fire that you cannot extinguish with water. Then we have several development already ongoing in this segment for this application. And then submersible vehicles like autonomous underwater vehicle. Some customers have already tested our cell at a depth of about 7,000 meters with good performance. So our cells are suitable, very suitable for this kind of application. And of course, aerospace in aviation, the lower weight of the battery allow to have longer flight time, which is important because otherwise this application might not be viable. So our focus is in unmanned aerial vehicle like high altitude pseudo satellite, the HAPS, regional air transport like 2 to 4 seater, but we are developing up to 12 seaters electric aircraft. and vertical takeoff and landing aircraft, which are the future of the urban air transport. And in the case of large commercial air transport, are the emergency power battery system, because of course a safety issue, which are devices into large aircraft. And a similar situation maybe is in case of a man-portable military battery packs, and we can reduce the weight that the soldiers are carrying, and also because of safety reason, because there is no explosions. Just to give an example of our development, we are currently developing here in Brazil, together with the Texas aircraft, the ECO, which is the electric version of this aircraft, a two-seater aircraft for training, flight training and regional transportation, developed and to be manufactured here in Brazil. And with our battery system, we will achieve at least 50% lighter the weight of the battery than the current lithium-ion technology, and this will allow flight time in excess of 2 hours and expected 80% lower operating cost. And with the further development of our technology, we will be able to increase a lot the flight time, maybe 3 or even 4 hours. I would like to talk a little bit about our product roadmap. Today we have the conventional liquid lithium salt system and 2 types of cell, one high energy cell and one high power cell. We are more or less here today, and we are aiming to achieve 450 watt-hour per kilo by 2025 and 500 watt-hours per kilo by, again, 2025. But in parallel, we are developing, we are focusing the development on the new generation of lithium sulfur system, which are the quasi-solid state, the almost solid state, and then to achieve the solid state, the all-state cell. And this will provide enormous improvement in the performance of the cells in terms of density, energy density. We are aiming to achieve 550 watt-hour per kilo yet at the beginning of 2023, and then reaching 600 watt-hour per kilo. And then with the solid state cells, we will achieve higher levels of gravimetric energy density, together with the cyclability and the temperature range. We're expecting to achieve 60 to 70 degrees of temperature. So talking about specific of the quasi-solid state system and its enormous improvement, as I said, the ultra-high gravimetric energy through high cathode discharge capacity with high sulfur loading. So we are talking about dense cathode. Standard cycle life through a new formulated electrolyte with no polysulfide solubility and reduced lithium anode degradation, and protected lithium anode technology. All of them are patented technology. And also we will have a broader temperature range. So it will be effectively enormous improvement for our technology for the application of our customers. This is what I've prepared for you, and thank you very much. You can see my email address. Feel free to contact me for further information on or doubt. I will be more than happy to answer. Thank you once again.
Thank you, Mr. Enzo. Some of you already saw my message on the chat. Please, if you have question, already advance in the chat, okay? So now I would like to invite Vera, engineer battery production at TMM, to talk about the niobium application for high energy and high rate lithium-ion batteries. Welcome, Luana. Your screen.
Yes, I'm sharing. Do you see my screen?
Not yet, Luana, but maybe it's coming. Could you try again? Now it's coming? Nope. Okay, all set. Go ahead.
I think it's okay now.
Yes, please, go ahead.
Okay. So it's a pleasure to be here today to share some advances and challenges regarding niobium applications for high energy and high power lithium-ion batteries. But first of all, I would like to say that niobium is not a hard metal, and your Earth's crust abundance is around 20 ppm, very similar to other metals used as raw materials for batteries, like lithium and cobalt. Then CBMM is the world-leading supplier of niobium products and technologies. The company was founded in 1955, and from 2011, 15% of its capital was acquired by a Chinese group and 50% by a Japanese South Korea consortium. We have a full integration of our mining to final products in Araxá, Minas Gerais. And due to because we have more than 50 years of investments in niobium technologies and its applications, resulting in currently more than 120 tons per year of ferroniobium equivalent production and 8% of the market share. In 2021, the investment in technology in CBMM technology program will be more than 2 million reais, 200 million reais. To support our partners and the road and the customers for sales and technology developments in more than 40 countries, CBMM has an office in São Paulo and 7 subsidiaries and traders offices in strategic regions of the world. From the technology program, efforts to amplify the application of niobium, in the last years, it was included in our portfolio of products new alloys and oxide products that can be customized in order to meet the specification requested by our partners. Niobium oxides are versatile materials due to their physical-chemical properties. Considering its pentavalence, niobium oxides can present different crystal structures, polymorphs, with specific and outstanding electrical, mechanical, chemical, optical, and magnetic properties. Then it's a quite interesting material able to fulfilling requirements of a wide variety of the applications, which included superalloys, capacitors, fuel cells, catalysis, sensors, and solar cells, and batteries. Considering the operation of a lithium-ion battery, we have named for a modern battery technology chemistries for anode or electronegative negative electrodes, such as carbon graphite, lithium titanium oxide, niobium titanium oxide, silicon graphite composites, lithium metal, and composites using graphene. For cathode or positive electrodes, we have materials as lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, lithium nickel manganese cobalt oxide, lithium nickel cobalt aluminum oxide, the high nickel materials. Driven by the intensification of discussion about the electrification, the growth of the electrical vehicle market, the demand for high energy density, fast charging, longer lifespan, and safer lithium batteries, lithium-ion batteries, has increasing the search for new technological solutions. The niobium is addressing the major challenges in materials chemistry to meet this demand. From the roadmap, we can highlight the main trends for high energy and high power batteries. For cathodes, initially the niobium doping of high nickel materials to increasing the stability and the safety, decreasing the cobalt content in the formulation. And in the long term, the use of the cobalt-free materials, cathodes, such as lithium-rich materials and manganese-based niobium-containing disorder rock salt structures that I will say after this slide. For anodes, in the short term, we have niobium oxide based materials with long lifespan and improved volumetric energy. And in a long term, we will have the development of NTO, niobium titanium oxide, advanced systems, as well the using of niobium graphene composites for fast charging. Last year, CBMM has made an investment for a minority share of 2GM company in Singapore, the graphene company in Singapore. So for cathodes, in the first case, niobium has been used to develop materials with high energy density and enhanced stability with low content of cobalt or even cobalt-free materials. In the first case, we have a cobalt-free lithium transition metal oxide that have been explored because from the understanding that more than 10% of lithium excess in the structure creates oxygen transition metal channel percolating network and induce the formation of the cation disorder rock salt structure. We can see in this figure. This modification can favor the lithium diffusion in the structure and increasing the energy capacity. The high energy capacity in this material is attributed to the combination of the metal, the transition metal, and the oxide ions oxidation in parallel reactions. And then in a solid state reaction, then we can see a charge compensation reaction because for the lithium excess in the structure. To balance this charge compensation reaction, you need a high valence metal, in this case, niobium. For this study, niobium increase the energy capacity of this material, almost double the theoretical capacity regarding only used manganese metal, manganese oxide. Then you can see in the table the material, this material, the study material, present a highly specific capacity compared to the L Nm, and other commercial cathodes. Based on the quite interesting results, it was performed in comparison with wildcat technologies, high throughput screening tests for studying two chemistry, disorder rock salt 1, disorder rock salt 2 here, of cathodes. The first material showed an energy density improvement of 13%, and the second one, with lower lithium content, 35%, when you compare the phase 1 and the phase 2 of the project. When you compare the price per energy of the second material, with low content of lithium, with other commercial ones, the disorder material number 2 here, the present are 40% and 47% cheaper than the NMC and the NCA materials. We can consider these disorder rock salt structures promising candidates for lithium-ion battery cathodes, but we have challenges yet related to the cycle life and the electronic conductivity. In high nickel materials, we have a high energy densities because for the nickel usage, but when you increase the nickel concentration of these materials, we have an increase of the reactivity of the cathodes, impairing its stability and the safety consequently. Choose the role of niobium in these structures is to increase the structural stability of the material, since niobium is not electrochemically active in the potential in the high voltages, and also aiming lower concentrations of cobalt in the structure. From this figure, it is possible to observe that both for NMC 622 and MC 811 under different conditions presented an enhancement of capacity in the green line, retention by niobium doping. Currently, you have worked with formulations with higher than 90% of nickel in the formulation, observed similar results for both NCM and NCA materials. In fact, we have now a paper recently submitted for publication in collaboration with Hanyang University about niobium-doped NCA materials. Talk about anodes or negative electrodes. New niobium-based materials have been developed as battery anodes because they improve the mobility of the lithium and the structure by creating spaces, resulting in high charge and discharge rate properties and high power. In contrast to conventional materials as graphite, that under conditions of fast charging can undergo the lithiation process, which can cause a short circuit and in the system, for example. This affects not only the stability of the material, but the safety of the battery. When niobium oxide is used with titanium, a new class of materials is created, showing approximately 3 times greater energy storage capacity than conventional materials used in LIBs. The resulting structures has a satisfactory intercalation properties, and moreover, the reduction potential for titanium 4 and titanium 3, it's very similar to the niobium 5 and niobium 4 at 1.5 volts. This increase the lithium amount per formula unit in the redox couples, in the redox reactions. NHO is a promised solution. However, considering the operation, the potential window, it's not possible to deliver the same level of energy as other conventional materials as graphite. But on the advances with NHO products, we have a collaboration with Toshiba, and has published a paper in the last month with Professor Goreneuf, the owner of a Nobel Prize in Chemistry in 2019. Niobium, and we have another class of materials, niobium tungsten oxide materials, that present open tunnel structures that are stable during the cycle and allow the lithium ions to circulate freely in the structure, being able to replace the graphite in the fast charging batteries. In general, this material works because there is a very smart structure with a balance of the expansion of the material during the lithium charging. And during the lithium charge. Like NHO, out of this material this material do not provide a high energy by weight as conventional lithium-ion battery. Then they have an excellent volumetric energy density and would also be more suitable for applications where space is more critical than weighting. Considering that these niobium features present today here, we can assert that niobium ends up poisoning to be a disruptive element for advanced lithium-ion battery materials. And we can talk more about this in the Q&A session. Thank you.
Thank you very much, Luana. Now we will have the Q&A session. So Luana, could you please stay, turn your camera on, and also invite Mr. Enzo to do the same. Okay, so feel free to send questions on the chat, and we will choose some of them to be answered live. Okay, so I already have some. The first two comes to Mr. Enzo. So one is from Hudson. He's going to talk about the comparison on power density of lithium, sulfur, and lithium. How is that today? I saw a slide, but you can comment more about this. Okay, Enzo?
Yes, for sure. As I've shown in my presentation today, when we talk about lithium ion, we have different types of cells and within the same technology, which is lithium ion. And we need to think of lithium ion as a technology that has more or less exactly at least 30 years old. So we understand that more at the end of these, the possibility to have a high increase in the energy density. And today what we are seeing that we are talking about 240 to 250 watt-hour per kilo in the case of NMC, NCA. And this is the reason why I said that our energy density is about twice this energy density. But if we look at the LFP or other types of cells, then we have an increase. This difference is even more. It's more than 3 times or even four times. And talking about the theoretical gravimetric energy density, we can reach even 5 times. And I think it's an important figure because we can understand how much we can improve. Of course, it is theoretical and practically it's not possible to achieve, but there is a long way in the development of our technology and to increase even higher level of energy density.
Okay, thank you, Mr. Ngo. Now I have a question from Max Borges, probably going to address to Luana. Luana, would it better for Brazil to embrace new technology as a protagonist of the current global momentum and soon then remain stuck in the pollution technology of the past that are being rapidly abandoned around the world? You talk about a lot of materials and technology, but he's talking more about the trend of the new clean technology for batteries. So you can talk a little bit more about that?
If this technology is clean for the future, it's right.
Not really, no. I think he's more interested in how Brazil is going to embrace this all new technology. It's basically what you said. The new research and everything that we are researching for new materials. You talk about nickel, cobalt, manganese, yeah? But we need to look forward for some non-rare materials. And I think the main goal for the future is to research material that will be available and you'll be not, we say, environmental friendly at the end of life of everything of this life. Okay, so you don't need to change from petroleum to another hairy or problem cause
it's
another.
not. Yes, you have today in our mind around 200 years of for supply the current demand at the same consumption rate from today. And niobium is a very friendly, environmentally friendly material. Now the extraction it's very good for you can see very good for the environment, and because you don't need you can need you don't need to explode the mine, and we have a lot of niobium on the earth crust, and our main goal using niobium is provide new technologies that can be more efficient and more stability. For example, the NTO technology, a development with Toshiba, can provide around 10,000 cycles of lifespan, and I think it's a good advantage for the recycling issues and the second life of the batteries. Ricardo?
Yes, okay. I just reading the question. Okay. Unfortunately, the time for the Q&A question is too short. Okay. I will stimulate if you saw some question, and if you can interact with the chat, you'll be okay. Okay. The question will be the problem will be in our time limit. Okay. So we have more 1 minute for each one, and I would like to use the final question for both. Okay. So, Mr. Say here. Marco Panzeri, okay, was original addressed to Mr. Pasquale. And what's your opinion, the trade between lithium battery for storage versus fuel cells for the power supply EVs? So I would like to share this question for you both, okay? And please be short to really go ahead with this panel, okay? And if you can direct with the question, I will be glad. Thank you.
I'm sorry, fuel cell, you said?
Yes.
Okay. Yeah, we're talking about the hydrogen. Yes, it's another technology and a lot of people is talking about fuel cells and the hydrogen. I think there is room for everybody in the market. I think that yes, they are talking, but I think it's something more for not for a near future. Maybe there are ongoing development, but I think there is some issues to be solved, even safety issue. But again, I think there is room for everybody. I don't think we are exactly competing. I think there is always trade-offs, and I think there is space for everybody. And again, I'm not seeing a competition between exactly a competition between fuel cells and our technology.
I have seen a lot of advances in in the hydrogen technology. Then I believe that the best way is the hybrid systems using batteries and fuel cells for the future. As Enzo said, not a near future, but I think it's a real future, because maybe in the 10 years ago, 15 years ago, it's not real for our scenario. And today we can see a lot of technological advances in the TV, media, and with our partners, OEMs and manufacturer partners. I think the best way is the hybrid system to meet the demand of the electrification of the electrical vehicles.
Okay, Luana. Okay, Enzo. I would like to thank you, congratulate you for the great presentations, and to help the mediator to fit time. Okay, it's a big challenge, but we need to move on. Okay, thank you. I stimulate the audience if you have questions, or maybe you want to schedule some meetings, send a mail to organization or to myself. I'm glad to arrange and to establish some kind of pause meeting and some kind of meeting to help them in projects, other future initiatives. Okay, thank you, Enzo. Thank you, Luana.
Thank
Thank
you.
Very
you.
much.
It was a
Bye.
pleasure. Pleasure. Goodbye. Goodbye.
Okay, so now we will start the second panel. It'll be a very fast event. Okay, so the first presentation will be battery cell chemistries. What is the future? By Mr. Greg Harris, Global Strategy Lead for Electrification at Horiba Maida. Welcome, Mr. Harris. It's your time. Thank you.
Thank you very much for the introduction.
Share your screen, please go ahead. I will let you know when we are seeing. Mr. Harris, you are here? Mr. Harris, can you hear us? Ivan, maybe can switch to Mr. Hudson. Can
I am good to go here if it's necessary.
okay? Looks like we have some problem with Mr. Harry, so we can swap it between Mr. Harry and Mr. Hudson. Hudson, you are ready?
Yes. Yes.
So let's introduce yourself. When Mr. Greg Harris is we're going to change just the order, okay? So I would like to. Okay, Greg, you back?
Yes, apologies for that. I don't know what happened when I went to present. It just cut me off.
No problem. Okay,
Can
so
you
try
see?
to.
Can you see my screen now?
No, that's okay. Go ahead. So just try to share your screen. Not yet. Okay, go ahead, please.
Okay.
Thank you,
I
Greg.
still have the music playing as well. I don't know if someone can turn the music off. I still have it playing in my headset. Everyone else has left me.
Greg, you are in mute, I think.
No, I'm not. Can you hear me?
Now I can hear. When you are in presentation mode, I was not listening you.
Very good. Not very handy. Give me 1 minute. Do we have the presentation now?
Yes, and your voice is okay. Go
Okay,
ahead.
thanks. Okay. So apologies for that slight technical issue. I'm just here today from Hariba Myra to talk about battery cell chemistries and some of the future technologies. Obviously, we've had some excellent presentations from the other presenters already, and we will have more going forwards during the rest of the day. However, we come from a slightly different position. Hariba Myra is an independent engineering and testing company. And as such, we don't manufacture cells and we don't have any particular adherence to particular cell technology. So what we do is look independently at technologies that are available today and those future technologies and where how they can be utilized in particular applications. Today I'll give you a very brief, because of the timescale, but a short presentation at customers in this area. So from a high-level perspective, we see there are, I think that in the first presentation today, Jay Nagley actually talked about these targets, very similar targets that were set by the UK's automotive industry. And in fact, I think these are very relevant targets as well for the global business for electrification. So looking at those key areas of cost and performance, safety, recyclability, predictability, things like thermal runaway. These are all areas that everyone is focused on addressing with the current cell technology, but also considering how new cell technologies will be better able to meet some of these targets. But the reality is today that the current cell technologies there are still significant gaps, and therefore I think it's generally understood that that there'll be a requirement to develop beyond lithium ion phosphate, nickel manganese cobalt chemistries to be able to achieve and go beyond these targets in the future. So as we see, as I just mentioned, if we talk about the current cell technologies, this compares the gravimetric performance of different types of batteries for applications. And you can see on here a number of the key manufacturers: Panasonic, CATL, SDI, so and predictions for they plan to get to with their current technologies. And as you can see, there's still a gap. It will only go so far achieving the targets that are right parallel to so summarizing the different technologies. So recently we've gone through a whole assessment of experts, our scientists and engineers have been reviewing current technology in the market. And this is a very, I'd say, very brief summary of some of the outcomes of that report, which considered all types of constraints of different types of chemistry, and looked at how those chemistries will go forwards. So basically, yes. Hello.
Sorry to disturb you. To interrupt you. Your audio is coming too cracked to us. I suggest to you if you can turn off your camera and just use the audio. Maybe try to improve it. Okay.
Also, in my headphones, I have the music playing as well. I don't know why. It's not very helpful.
No, now it's okay. It's very good now. Go ahead.
Okay, right. So as I was saying, when we look at, so we've been undertaking this assessment. We've been looking at the variety of different chemistries and major technological developments as well, and looking at those applicability for future application into both passenger and commercial vehicles. And as you can see, really the green is showing when we see that technology being most useful, through amber and red, where that chemistry is still unlikely to be applied in that timescale. So, as you might expect, still see lithium-ion in large scale automotive application dominating until really for the rest of the decade. But then as we go beyond that, we can start to see other technologies coming in. And obviously the most sort of significant for general automotive use will be solid state, assuming that the the major technological difficulties can be overcome for that. There's also certainly a place for lithium sulfur, as we heard from my colleagues earlier today in the presentation, particularly in applications where perhaps we're looking at things like overhead charging technology and the ability to put very fast charging into relatively small batteries. So there's a number of different technologies we can see here that can really how will play a part going forwards, but obviously as we get beyond 2030 it becomes far more difficult to predict exactly how those technologies will be adopted. And looking further into wider ranges of alternative chemistry, lithium metal again can start to play a part as we move forwards, assuming that the the solid state electrolytes can be utilized, and looking at niobium-based technologies. Again, we heard about that technology earlier today, already available and being adopted, but its particular properties make it particularly suitable for certain types of applications and not large volume, relatively low energy and mass energy density. So what we do see is the adoption of high nickel cells being the key choice in the short, medium term. But other technologies, as we can see, could be more successful or combined with things like high nickel cathodes to improve the energy density, as well as address some of the cost and safety issues going. So, just briefly, only cover again with a limited time scale. Mentioned solid state being one of those key technologies going forward. Some of the major benefits, obviously, address the safety issues that we see, and this technology well um, that we're seeing, but at the end of the day, it still has significant technical to overcome. That being adopted, as we said, sort of 2030 onwards into more mainstream applications. One of the challenges here is to achieve the full energy density potential by taking out the inactive weight of the cell. So just a brief summary, really, as we see things in the near term, in the next sort of 5 years, certainly the current lithium-ion technology dominates. NMC has been the strongest chemistry for passenger commercial vehicles, but actually we now see the resurgence of lithium-ion phosphate because of the focus on cost. Adaptation being made to move to optimize the design of max technology. The medium term, start to see new cell see like size solutions. These are so these are very brief extracts from technical papers and interesting, and people like to see detail behind this and a lot more information besides on the specific chemistries and their challenges and the perspectives on their future adoption, then please contact me. We can that report is available for purchase. So just following on, really, just to give a bit of background around HORIBA MIRA. So we've talked about cell chemistry specifically. We're, as a business, that's just one small part of what we do, but electrification is very much key to our overall business in terms of providing engineering consultancy and testing services to the automotive sector. And although based in the UK, we provide those services around the world to customers through our local offices. For example, we have a HORIBA office based in Sao Paulo, and my colleague Leonardo is joined the call today. So we do work with customers around the world to provide our services and our capabilities. We have a lot of experience in developing batteries for all types of application, and we're very much focused on the approach of using understanding those technologies, being able to as and optimizing the system. For example, approach customers to identify the ideal technology, the architecture and system requirements, focusing on areas such as the thermal system and battery management system, and then completing our capability overall in terms of the So we also have a wide range of testing capability, and time I'll speak through this, but we're able to support customers and off batteries with whatever battery cells use. So thank you very much for your time.
Thank you, Greg. I would say that your audio was not so good to us, okay? During this time, I would suggest you disconnect and connect again to try to improve the internet connection and check the microphone, okay? Thank you very much, okay? So now I will invite Mr. Hudson Zanin, manufacturing group at the Unicamp Advanced Energy Storage Division, to talk about supercapacitor. Welcome, Hudson. Yes. Can you share your screen, please?
Yes, I'm trying to. Can you guys hear and see me and the screen?
Not yet.
As well?
Not yet. Now it's okay. Okay. When you are ready, can you start?
Okay, so I'm good to go. So thank you very much for the invitation. It's a pleasure to be here and to hear all the presentation here about batteries, and could add something about supercapacitor, which is not a competitive device, but a complementary to a battery. So when you look from the outside, all devices could look like the same. You could not distinguish a supercapacitor from a battery itself. But when you look from the voltage time loops and graphics, you see they are completely different. Battery used to provide a constant voltage to the cell, constant. Supercapacitor, you have the dV/dt, the variation of the voltage with time constant. So the voltage change along the charge and the discharge. Also, the supercapacitor have a very low equivalent series resistance because it's a power system, and because of that, it's charged very quickly in order of few seconds, and discharged very quickly as well. And also, a great advantage of a supercapacitor is the amount of cycle they could provide. The colleague here, Luana, I guess, she said that a great battery have a 10,000 cycle. We are talking about here 1 million cycles for a supercapacitor. So, but let's have a look on the Agm plot. This is a typical plot on the energy and the power of the systems. So you see a supercapacitor have much higher power density compared to batteries in general, and that's very interesting for several applications. But the energy is much lower. So let's talk first about how supercapacitor could be charged extremely fast. So basically, let me introduce you. Let's start from a conventional capacitor where you have two parallel plates separated by a dielectric. And this system, if you polarize it with a negative potential and positive potential, each plate of the device instantaneously is charged with the same potential, because it's a potential. For example, if you apply a negative potential, the electrode will have a voltage on it, and the dielectric inside the cell instantaneously have a positive charge on this phase here, for example. One phase of the electrode, and the other one, the opposite happens. So you have two capacitor in each electrode, and the system have a small internal resistance, so you could treat this capacitor as a two capacitor in series with resistance. So this is a conventional capacitor. What we want is a supercapacitor. For that, we change the dielectric inside the cell. Instead, use plastic. We use water, which have a much higher dielectric constant, and we use organic electrolyte, for example, and we really increase the surface area with a porous material, ultra high surface area material like activated carbon, for example, which have about 2,000 meters square per gram, and this is a huge surface area compared to the conventional surface area, flat surface area. And also, we reduce this distance here. We have the D is related to distance by absorbing ion on the surface in this ultra high surface area material. And that we reduce this parallel distance between the electrode for a nanometer size. So basically, a supercapacitor works like this. We observe ion on the surface on the material, and we have what we call electric double layer capacitor, the charge in a few seconds. But also, we want to increase the energy inside a supercapacitor, and in order to do that, we use two tricks. We apply, we combine this carbon-based material with metal oxides to have an ultra-fast redox reaction on the surface of the material. And also, we try to play with a very interesting material that's allowed ultra-fast intercalation process. So the materials we work here at Unicamp is almost activated carbon for the positive electrode, and that we produce this by biomass carbonation. We make a cocal, and then we activate this with CO2 or water. So in a very simple and cost-effective way. We also use graphites and treat this to make graphene and all this kind of material. And combined with more noble materials like nanotubes, which we produce here with ethanol-based material, which is cheaper as well. So we combine this kind of material in a negative electrode, for example, with niobium pentoxide, with manganese or nickel oxide as well, to bring Faraday reactions to the system in a very peculiar way. So what we are trying to do here is use basically the ideas of a supercapacitor, very charged fast system, and bring some components from a battery and try to make to combine this device. So that's the main idea. So we want to increase the capacitance of a supercapacitor and the energy inside of it. And also we want to make use of materials that we have inside a battery and make it charge faster. Is that possible? Is that possible to have a device that could combine both of device? So I'm going to present to you guys very quickly here an example what we have been doing here at Unicamp. For example, we combine here on A and B carbon nanotubes with activated carbon and produce a positive electrode. And then we combine here C and D on the negative electrode nanotubes with niobium pentoxide particles. We have published at least 2 papers on this direction using aqueous electrolytes, which are much more cheaper and easier to handle low toxical than organic electrolytes. And this data I'm going to show you here today is relating organic electrolytes, which have a much wider voltage window, and we could store more energy on this. So basically, the configuration of the data I'm going to show very quickly here are producing a coin cell just like this one here. So you have a positive, negative electrode. We have a membrane, which is electrical insulator, and allow the ions to be exchanged on the through the membrane. So as you see here, for a conventional capacitor, we expect it to have like a very rectangular voltammogram, and we do not have this one here on A, and we have a combination with some redox process that is you see this loop here on the CV on letter A. On B, we have impedance spectroscopy, and what we expect from a battery is basically 2 semicircle. And what we have here, we have a combination of semicircle and a straight line up. And if this straight line up is very sharp to the top, parallel to the y-axis, is a conventional capacitor. So this is a conventional capacitor. And taking a look what in letter D here, we have something that Luana present us somehow. I didn't know if she's going to present it, and that's great because we are in consonant here. We use this niobium oxide material with the nanotubes, and we observe that as we cycle the cell, the lithium intercalation become much easier to happen. And just to go quickly on this, because time is short, the letter G, we have the charge on the button on the left. We have the G, we have the charge-discharge process of a supercapacitor. As you see here, we have the voltage change as I started the presentation today. We have the voltage change almost linear to as the time change. So that's a capacitor. So basically, while the first attempt we did, we have not the best of the both, but the worst of the both. If you see in the letter I here, you see here on I, you have the green line, which was our first measurements, first results, where we have a capacitor that does not have as much as energy, as much power as a conventional supercapacitor, and that battery that not have as much energy as conventional lithium-ion battery. So as we improve by combining, reducing the size of the particles, improving the amount of the niobium pentoxides and the carbon-based material, we move to the purple line here on the bottom right side of the system, where we have the best of the both, ultra-fast charge process with a much higher energy than a conventional supercapacitor. So just a quick look on the impedance. A supercapacitor have a straight line up, just like this first figure here. This is a impedance data, just a draft, of course. I did myself here very quickly for a capacitor we produce here in the lab, or the same, almost all the capacitor we produce have this kind of shape. And when we produce a battery, have this kind of shape. We have two semicircle and a straight line, 45 degrees, which is a transport limitation. So that's what we have at the end of the day, combining supercapacitor features with battery features, and we are saying here that's possible to be done. So we start with the green, and then we move to the purple line here. So we analyze all these kind of cells in the two ways. After first measurement, we do manufacturing, and we also do a very basic science, which is operando analysis. I'm going to explain quickly all these two guys here. At Unicamp, you have a manufacturing. You see on the YouTube link here down there. I'm going to put this on the shot if you want. So basically, what we do, we have a setup preparing a coin cell. If it's work well, we move to the pound cell system. We put like a 32 system on parallel, and we start doing this year during the pandemic, and hopefully in the 3-year time we are going to be able to produce these modules. We have done a very short example here in our lab, but we are just in the beginning. So that's the picture of our manufacturing. Basically, we prepare a coin cell, then we move to a bigger cells, just like this pound cell in letter H. We produce here at Unicamp. So we make an ink, coating, we dry the coating, we cut in the shape what we want. We have the shape, the pound cell shape, we align the cells, and then we, after aligning the cells, we and separate by a membrane to avoid short circuit. We made a welding, and then we make a case to put all inside, and then we fill with electrolytes. So where we want to apply this, we are just submitting a proposal to Fundep, Rota 2030, where we want to combine a full cell with a battery and use a system like we have a conversion of electricity inside the car or a van. Basically, we fill the tank with water and ethanol. Here, what we have a lot in Brazil, we have all the infrastructure ready to go. And then we use a fuel cell and maybe a reformer to produce hydrogen. And then the fuel cell produce electricity inside, which move electric motor and which charge batteries. We are also doing batteries and supercapacitor here, not just lithium ion, but sulfur as well. And this is the application we are working. So we go to a very high models, packets. And then we also do a very basic science where we shine lines, synchrotron lines, lasers, all this kind of stuff to see how the electrode and the electrolytes change as we charge the cell. So I'll just give you guys an example here where we charge and discharge a cell with this kind of system. We have a positive, have a carbon, high surface area carbon, activated carbon on the positive electrode, and we have multi-wall carbon nanotubes with niobium pentoxide on the negative electrode. And we see here how the spectra of the electrode change as we apply voltage. What happened here is we didn't combine 1 and I, but basically what we find is just like that. While we have a niobium pentoxide, we have this orthorhombic crystal structure, and we have this channel in the middle where the lithium ion could go through it. And it's possible because to these added effects relate to the niobium pentoxide edge defect bounds. So basically, this lithium ion, for example, sodium ion, are very small in our order of a few nanometers. And this is interplanetary space here from the voids of the niobium pentoxide, for example, is 4 angstrom. I said nanometers, but it's angstrom, okay? Sorry about that. That's what happened here when we separate the cell, the lithium ion get in, or the sodium ion. The same happened with sodium. The sodium ion get in the system, and you lose this main high frequency and middle frequency relate to this voids process here on the niobium pentoxide. So we see here on the chart, and we see this one here on the discharge, and we see the reversible process. And this kind of system, we have not only electrostatic process, but we have pseudo-capacitance, and this took quite a lot of to be charged. And we, for example, have cells with more than 300,000 cycles already performed. So we are moving to, and the efficiency of the process is about 93% in this kind of system here, which is much higher compared to conventional battery. What I'm trying to say, that is a complementary device to batteries. And that's it for now, folks. Thank you very much for listening. I would like to thank you, FAPESP and Shell Oil Company, for funding us. And I'm going to put on the shot the 2 YouTube videos relate to our manufacturing, and also to the car that we have. We participate on the fuel cell and the battery system. I've shown you in some of the slides back there. So thank you very much for listening to me, and I'm open for questions.
Thank you very much, Professor Sanzani. Now you have the Q&A question. I can ask you, Greg, you are back, so you can turn your camera and microphone to see if your voice is coming better now. And Mr. Hudson also. Feel free to send questions on the chat. We will choose some of them to answer online. Okay, so we have already one from Luis de Carvalho, probably to you, Greg. You know the dilemma of the batteries? Yeah, you are listening?
Yes.
Okay. We know the dilemma of the batteries is to integrate the cycle life, energy, gravimetry density, speed of change, and thermal stability in these items today. Is work safety the biggest challenge. It's cover a solution that maintain of the equilibrium of its. I would like to comment from you, Greg, about this. The cycle life, energy, gravimetric, speed of charge. Maybe you can help him.
Yeah, so he's absolutely right. Today, it's very difficult to achieve that perfect balance. We have a number of competing technologies, and depending on the application, it's important to you have to select the best solution for that particular application. So I think I didn't, obviously, apologies to people. I know that you couldn't necessarily hear me during the talk. There's some problem with the audio, but I explained there how we approach every application by really understanding the specific requirements and then looking at the most suitable solution, and thereby you have to decide with a compromise of life, cost, thermal performance, etc., and then look at how the system solution would be best to meet those. Going forwards, going forwards in the future, there'll be the solid state has a lot of potential to actually resolve a lot of these issues, and in combination with those different cell chemistries, they will hopefully enable those cell chemistries to be able to compete and actually go far beyond the current NMC and LFP, which at the moment generally offer the best combination of those elements in automotive applications.
Thank you, Greg. Now your audio is perfect. Okay. We have a question from James Hobson to Hudson. Okay, which market segments look the most viable for a best of both for supercapacitor system? Do you think this approach can accelerate adoption of some cell chemistry with power limitation? Hudson, before you will respond this one, I would like to add my comments also. I call this a hybrid solution, right? When you combine supercapacitor with the conventional batteries. Do you know the economic rate when is going to be really feasible to really mix this, when the price of the density energy for supercapacitor maybe is bigger, a little bit bigger than the battery cells, but when you think you'll be able to economically try to really implement that? Okay, your turn.
Well, thank you very much, guys, for the question. And my point of view is just like that. Lithium-ion battery, we have almost 1,000 players all around the globe, and let's say maybe 10 players in the supercapacitor side, maximum. Okay, and my point of view is just the price is related to the this question: how many people are doing the job, how many players we have. So at the moment, I believe that battery price is cheaper than the supercapacitor because of that. And Maxwell, for example, one of the leaders on this segment, are doing very good job when they're combined both device. But the market demand, most people doesn't know really well supercapacitor, especially this pseudo capacitor. We call pseudo because it's a pseudon of a fake. It's not just capacitance, but have Faraday process inside as well as a battery, but a very specific Faraday process. So in my point of view, the price could be as cheap as a battery if more people are doing this. And we are doing this in a Unicamp in a very, let's say, a lab scale. And there is a electrochemistry guys doing 3 electrodal cells. We are doing this in a coin cell, in a pouch cell, and we could produce like a few cells, only 2, 3, 10. Let's say maybe 100 cells. It's very low amount, And for example, in Brazil, we don't have any intention at the moment, as far as I know, to have industry on this topic. So that's why I'm here. I'm here to explain to the engineers, to the people that could take some decisions, that a supercapacitor could be as good as a battery, especially if you are looking for a power density system, ultra high power density system, where you want to charge very quickly. Let's say we are talking about 10 seconds for charging. We produce electric bike here at Unicamp, and we charge this in less than 5 minutes. And that's a very interesting, something we want to show to the guys on the market. We are researchers.
Thank you very much, Hudson. I apologize for you guys both. Okay, thank you and congratulations for the excellent presentation. It's more technical. Besides some technical audio problems, Greg, we were able to solve your PowerPoint presentation. So, as I said before, this is the first one. Okay, we incentivate everybody to maybe send a comment, send a question, and when we're going to try to put everybody together with some meaning. And especially for Horiba Mayra, we have Leonardo Gigio, Nicolas Penoff already in Brazil, so they also can support anything else here from Brazil. They are located here. Okay, so Greg, thank you. Sorry, we must move on to try to keep it everything in time. Thank you very much. Okay. So for the third panel, I would like to invite the first presentation from Mr. John Fox from AMTE to talk about ultra-safe battery based on sodium-ion. Welcome, Mr. Fox. You are ready?
Yes, good afternoon from
Okay.
a very warm and, well, maybe not as warm as Brazil, UK. So I'm going to try and share with you.
Yes, your presentation already come. It's
Yeah.
your screen. Thank you. Go ahead.
Hopefully you'll be able to see my screen. And if you're cool with the opening slide, I'll just go straight on, and I'll try and keep this to the 15 minutes that we've been allocated. So I am John Fox. I'm the Business Development Director and one of the founders of Empty Power. And Empty Power is an unusual battery cell manufacturer. I want to say unusual. I'd like to give you a bit more information around that. And today, whilst I'm presenting to learned engineers from the Society of Automotive Engineers, I would like to just say, first of all, I'm not an engineer, I'm not a chemist, and I'm not a physicist. So any other questions I'm happy to handle. But if I can't answer the question from a technology perspective, I can certainly get you the answers from our wider team. The purpose of my presentation today is to cover 4 areas. The first is to give you a bit of background and introduction to Empty. Some of you may know us, those that don't. Hopefully it will give you some food for thought. It will talk about our strategy and where we're taking our products, and then into which markets and applications we're bringing those products. And ultimately, whilst inventing good, unusual products is one thing, you should also hopefully have a way of scaling those up into the volume markets as we see this great world of electrification take its lead. So to the first instance, we are a real company. We have a real manufacturing facility. We have effectively a mini gigafactory. And what I mean by that is our history of manufacturing is endemic in the world of lithium-ion batteries. And I'll talk about the history of our business in a bit more detail. But first of all, I'd like to just pose the question. If we were to step back 20 years and say, what's the best way of building an electric vehicle or a electric drivetrain, If someone was to come up and say, well, let's build it with a battery or a cell that was designed to power a camcorder, we would all think that person is crazy. But the reality is that's where we start and that's where we come from. Lithium-ion was originally developed for camcorders, and we've just reused and repurposed its technology into new markets. That's left us with a dilemma in the business, in that we now find people using, the wrong product in the wrong markets for the wrong applications. And what we're trying to do is change that by offering alternative products for alternative applications that are better suited. Now, as a business, as I said, we go back in time to the start of lithium-ion, and just to demonstrate how long this journey has been, it's been about 30 to 40 years, just under 40 years now, since the Oxford University team in the UK invented lithium-ion chemistry. And the first step in those days, the UK government licensed that patented rights, or the right to use, out to the Sony Corporation of Japan. And they came up after a period of time working with Oxford with the lithium-ion cell as we know it today. And clearly we've seen this journey develop along different chemistries and different processes. But along that same journey, there was a company formed called Agm Batteries. And Agm was a predecessor company that we ultimately bought. But its history is defined in lithium-ion cell manufacturing, as it was originally owned by the UK Atomic Energy Authority, and along with GSU ASA and Mitsubishi Materials, their purpose in life was to see how they could develop and build alternative products. We bought the business ultimately that had traded and had got to a position in 2013. And we bought it with a vision to launch new and innovative products that would be better suited for some of the applications that we foresaw coming in future markets. So to that end, our flexible manufacturing facility was repurposed, and we started to look at how we could commercialize new products, bringing new IP and new technology through to the market. And one of the good things was we met in early days with an inventor of sodium-ion technology, and that inventor of sodium-ion gave us the license, or we procured a license, and we now have the rights to manufacture sodium-ion cells in volume. And we'll go on to talk about the volumes and the timelines on that a bit later. But today, Agm Power, having grown from a private company, in February of this year, we announced our stock market flotation. And we are a fully listed company on the UK London Stock Exchange. And the reason for us doing that was so that we could gain a wider investment audience that would help support our future plans to build out gigafactory volumes for our products. And I'll talk about that in a bit more detail as we go through. In terms of the product set that we're going to be bringing to market, we will bring initially 3 or 4 variants of lithium-ion and sodium-ion products. Those products will start with a ultra power and an ultra high power product, and these products will have the capacity to be able to discharge at very high C rates. So we'll be able to see these going into applications that require very high power discharge, and we're now even seeing discharge rates of up to 100 C. So we're seeing very high discharge rates and high capacity to be able to dump energy. We've got an energy cell, which is going to be available in a 21700 format, and we're also taking out what we call ultra safe, and that's where our lithium ion then trades off and becomes sodium ion. So those product sets will be available. They'll be available later this year in initial volumes, and we'll see volumes grow as we build out our production capability. In terms of markets, the ultra high power cell is very well suited for hybrid applications, for vertical takeoff drone and performance vehicles. And we're speaking, as you can appreciate, to a number of the larger OEMs who are looking for differentiation with their vehicles and their product sets. Our energy product is good for let's call it standard automotive applications, those that aren't looking for explosive acceleration, and also for energy storage markets. And again, that's in a 21700 module. And we are also expanding that into 26650 and potentially larger, what's often referred to as Coke can design, which is gaining a lot of interest currently in the market, given Tesla's recent announcement about its formation and size. In addition, we hold some license and patents around a called Prime, and that's particularly well suited for the oil and gas industry, but also extreme conditions, and those are again available. And then our favorite subject matter of today, our ultra safe product, which is on it has interesting characteristics that I'll to talk about. In addition, so building a Australian an ultra storage product, and that classic LFP technology aimed at stationary markets. So it's a little bit ultra safe. Ultra safe is a product that we have developed with the manufacturers. That is currently available in what we call EHEV application size. It has a nominal capacity of 30 amp. Mine has a slightly less voltage range, nominally 3.1 volts. And the gravimetric energy density, whilst that's the holy grail for many, is competitive. And when I say competitive, it that the existing application in or battery use in some of the storage, the telecom towers, the low-speed electric vehicles is actually lead acid, and lead acid is watt hours per kilogram is measured at between 50 and 70. So in terms of our application, you wouldn't put this in your high-speed electric vehicle where you're looking for mega performance by any means. But if you're looking for a low-speed electric vehicle, maybe a three-wheeler vehicle or a small passenger vehicle, then it's absolutely fine. Currently, we're achieving 140 watt hours per kilogram. We see that going to approximately 160 watt hours per kilogram as we optimize and deliver through. So an interesting and exciting opportunity for many. One of the key aspects of it, at a bill of materials, the materials are 40% less at cost than a lithium-ion equivalent. So it starts to be competitive. And some of the things that we're doing is we're stripping out copper from the electrodes. The electrodes are built on aluminium on the anode and cathode. And that obviously has a knock-on effect to the cost build of the product. One of the key benefits, and while we call it ultra safe, is it also doesn't suffer from thermal runaway in the same way as its lithium-ion partners. So there are some very good applications for this product, and some that drive very good safety aspects. One of the other key aspects of it is also you are able to take the product down to 0 volts and recharge it from scratch. So it's a very good product if you've got it in a UPS application or applications where the users may not necessarily look after the product as well as they should. So our industrialization plans, well, that's all part of making this product. Our products are currently built in our existing facility in Scotland. We are doubling the capacity in that facility over the next 18 months. The UK government has been very supportive to companies like ours, and have also recently opened a new facility, which is a small single-digit gigawatt-hour capability, and we'll be using that to develop our products out. And then we aim to bring on during 2023 to 24 our own gigafactory in the UK. Our volumes, whilst they will be modest by comparison to some, will be in up to 5 gigawatt hours, and may include additional volume as and when we get the offtake agreements from our customers. So in 15 minutes, hopefully that's given you sufficient of an appetizer. We were never going to serve you a full meal, but hopefully as an appetizer, you'll recognize how we are leading the way with innovative battery cell solutions. And we'd love to talk to you if you feel that you have a requirement or just like to understand more. I'm more than happy to take those questions and reply to you accordingly. That's it from me.
Thank you, Mr. Cambox. Yeah, it's a real appetizer only, okay? But there is a time just for a short dessert, okay? So I would like to invite Mr. Felipe Miguel Casapo, Director of the Electrochemics Innovation Institute of Senai in Curitiba, to talk about smart energies, the imperative of innovation for sustainability. Please welcome Mr. Casapo. Can you try?
Yes.
Okay.
Hello,
Okay, you are ready to say? Yes, go ahead. Thank you.
My pleasure. Well, good afternoon and good morning for those of you who are in Brazil. It is my great pleasure to be with you today, so thank you for having me. I've been learning a lot this morning with everything that has been presented, and it is very an honor for us to contribute and to give some insights, some ideas on what we've been working on at the Innovation Institute of Senai in Electrochemistry for fostering the electric, smart, sustainable mobility of the future. So today I want to address you with the idea of fostering together the development of smart, sustainable energies for a more sustainable future. In order to do so, I've prepared some contents for the next more or less 10 minutes so that we can go to question afterwards. I'm not also a technical person, right? I'm not a researcher, so I will do my best to address the question afterwards. But if there are some questions I'm not able to answer, I have researchers working with me that will be more than glad to complement what I can say. So I got a bunch of general information about the Innovation Institute I represent today in Brazil. And what is very important for me today is to try to discover with you where we can collaborate, where we can work together and develop projects together. And today I want to address 3 technology trends that are important for us for the sustainable electric mobility of the future. I want to talk about batteries. It is very important, the question of energy storage. But as it has been presented before, I also want to address some question on supercapacitor, because we also need power beside energy storage for our sustainable vehicle of the future. And as we need to be as sustainable as we can in terms of energy storage for mobility, I also want to address fuel cells and maybe try to show how bringing together batteries, lithium-ion batteries plus supercapacitor plus fuel cells can help us designing the future we desire in terms of sustainability for electric mobility. So as I mentioned before, we are located in the city of Curitiba in the south of Brazil. This is where we are. So you can see here a map of Brazil, and you can see we are close to Uruguay, Paraguay, and Argentina in the south of the country. We are located in the quite green place of the city called the Botanical Garden. This is our building here. We belong to a national network of research and development, which is the Applied Research and Development Facilities of SENAI. SENAI in Brazil stands for the National Service of Industrial Apprenticeship, and it is nowadays a big network of applied research and development, which is composed by 27 institutes. So this is important to be said, just to let you know that we are part of a larger network so that we can develop more complex projects. For example, when we deal with energy storage, it is important to have artificial intelligence, to have machine learning, to have battery management system, and not just only the batteries, right? So we can complement our own competencies in electrochemistry with other competencies in, I don't know, data gathering, big data, artificial intelligence, in order to really produce complete solutions of research, applied research and development. These are some information on our institute, just to give you a glimpse, an idea on what kind of structure we have. We have a 2,400 square meter applied research and development facilities in the city of Curitiba. We work with more than 70 researchers. This number can change because we work a lot based on projects. So we have a lot of researchers that join us for a specific project, and then the amount of researchers can change with time. And we are currently managing a portfolio of $5 million in research and development with companies. We only work in applied research and development. All the projects that we develop in smart energy, smart materials, we also work with biosensors, are linking to the needs of industrial company. And today, our principal cooperation interests are in disruptive solutions for energy storage and also in smart nanomaterials. You have my data here. Afterwards, you can get in touch. These are some pictures of our institute. Now let's get started with the major content of this presentation today. So as I said before, we believe that a sustainable future requires a hybrid solution that will involve at the same time energy storage with lithium-ion batteries, but also power storage and power delivery with supercapacitor. And this has to be done with a lot of sustainability, with the most sustainability that we can. And that's the reason why we believe that fuel cells are also an important component of this hybrid system, where we'll have together lithium-ion for storage, supercapacitor for delivering power at certain moments of the driving, and then fuel cell for the overall clean energy focus. So in terms of developing lithium-ion battery, we have been implementing inside of our institute the overall value chain of the development of these batteries, in the sense that we work with the materials. So it has been said before by CBMM, which is one of our strong partner. We can use disruptive materials and what is called rare earth materials, such as niobium, for example, in order to improve the quality and the energy storage of our batteries. So this is what we've been doing. We have been working with new materials, disruptive materials, so that we can develop our own cell components, our own cathode, anodes, electrolytes, the overall package, to have our cells and our battery pack. Another important thing that has been important for us is to think about the overall life cycle after the use of the battery. So how we can reuse the battery in other purposes. We are calling that repurposing the batteries, and also how we can recycle with hydrometallurgy and reuse the materials once the battery cannot be used anymore. This is our plant, right? We have our own pilot plan for developing pouch cells units, prototype pouch cells units. This has been implemented very recently by the beginning of this year, and nowadays we are able to produce our own pouch cells, lithium ion batteries based on, for example, niobium. Another topic that is interesting us a lot are the supercapacitors, because we know that the lithium-ion batteries are important for energy storage, but they do not deliver the kind of power that is required in order to have a car, right? In order to give the proper experience of car driving. That's the reason why we are working also on supercapacitor, as it has been presented before by Unicamp, actually, in order to create electrochemical solutions that are hybrids, the ability of storing energy, and the supercapacitor that allows us to deliver power. More power with less storage of energy is what a supercapacitor can offer, and more power, less power with more energy storage are where the battery can be used. Finally, and this is one very important field of applied research for us, we are working on the renewable side of energies and trying to develop fuel cells where we can internally reform ethanol in order to produce hydrogen from ethanol, and then with the electrochemical process convert the hydrogen into energy. And our main concern in terms of research right now is to create the catalyst layer in order to allow an internal reforming of the ethanol in order to obtain the hydrogen. And that's a big question, because right now all the fuel cells that we have that are available in order to use hydrogen for electric energy production do consume as an input product hydrogen. And what we want to do is to use actually ethanol, which is quite available, right? And therefore to have an internal reforming so that ethanol can be converted directly into clean, green energy inside of our future electric cars. So it has been said before, the big challenge for us right now is the catalytic layer. This is where we are working, because this is where we'll have the internal conversion, right, of ethanol into hydrogen, and the rest of the ability of converting hydrogen into electrical energy is something that is already known, right, that is already available in terms of fuel cells. So our contribution right now is to develop the catalytic layer. And as you all know, we have already seen very good examples of fuel cells that are able to deliver energy in vehicles. So I have here 3 examples of Toyota, which are from the year 2020. The first one is an fuel cell that is able to deliver energy for boats, right, including transatlantic crossing. And the other one, the Toyota Hino hydrogen fuel cell for semi-trucks. Now, these technology, which are of course demonstration technologies, use hydrogen as the input product. As we said before, our main challenge and what we want to perform right now is to use as an input product the ethanol and be able to reform internally inside of our own fuel cell the ethanol into well, the final product, electrical energy for our vehicles. So the main conclusion I would like to propose, and this is where we want to collaborate and find some good partners, is that we know that the future is very linked to cities, smart cities, because most of the 10 billion human beings that we'll have in 2050 will live in big cities, right? In big urban spaces. And if we are not able to develop sustainable urban spaces with a lot of people living in, we won't have any sustainable future. And this is where mobility has to switch from the internal non-renewable energy and fossil energy burning inside of our vehicles to hybrid solution that will involve lithium ion batteries, supercapacitor, and fuel cells. And this is where we see a future for smart electric mobility. So that's it for me. Thank you so much for having me today. Thank you for your time. And I'm available right now if you have any question, if I can be helpful answering some questions.
Thank you so much, Philippe. Now we will have the last Q&A session. So I would like to John be back. He's already there. Please turn on your camera and feel free to send a question on the chat. What I was thinking is already started. So John Fox already interacted with Luis Sergio and already respond some question. I think everybody in the audience maybe has some Some highlights, John, you want to reinforce the questions that Sergio just said?
Yeah, I think the reality is it's probably easier to have a offline conversation answering some of these technical questions in detail. Coming back to my earlier point, the market needs products that are designed for the exact application. So, that's why we're seeing Tesla move into a different format and look to achieve different densities. And it's because they've woken up to this, what they're currently using maybe isn't optimized for their requirements. And I think the same is true of a number of the speakers today. We're seeing things like ultra capacitors start to play a role. And I think you called it earlier a hybrid battery pack. That's definitely coming. We're seeing OEMs considering that. As much as they're considering a hybrid ICE versus an electric support drivetrain, you're going to see a combination of different energy cells, power cells coming into packs to deliver the end requirement. So I think this is an exciting time for all. For me, looking at some of the markets that are, aren't as, let's say, fortunate enough in terms of volume and value, there's got to be other EV solutions out there that aren't necessarily involving, costly lithium products. Sodium brings a solution into that. I think of places like India and areas where two-wheeler and three-wheeler applications are dominant. You cannot cost in a lithium-ion pack of any size, considering the size of the vehicle. So I think, people, engineers have got to start looking outside of this, dare I say it, camcorder battery trying to fit into an application. So hopefully that's made sense and has not been too provocative, but happy to take additional questions if people wish.
I will be back with you, John. I would like to just two comments about the temperature. In the past, sodium has a bad reputation on thermal efficiency. Okay, but I'm also glad that you said in some slide that it's a PTC capacity. Okay, I will be back with you and I will interact with Philippe. Okay, think about it. Philippe, thank you for your presentation. I was able to visit this lab with Professor Marcos Berton almost a month ago. I was very impressed. I saw I think the first pouch cell prototype constructed on your lab. Okay,
Right.
and I'm glad that they already use the SAE for mobility, because SAE Brazil has a partnership with the FIEP and Senai Paraná ESI.
Right.
Okay, and I'm good to share with you because we try to put an electric tractor in the Jardim Botânico.
Right.
Unfortunately, we are in the lockdown. Okay, so we are looking for Otávio, Valerio, and maybe you and Marcos can help to maybe test some battery packs, new technology, everything with CDMM, with Oxys. So it's a very exciting moment we are living today. Just we are a little bit put on hold because of this pandemic, okay? But
Right.
everything is okay. For you, I would like to say fuel cell, great, is something that is totally different from Brazil. The SFLC, okay, for the ethanol and electricity. But I would like to talk about energy versus power.
Right.
Okay, so what do you think will be the future regarding?
I can't hear you anymore, Ricardo. Sorry.
Ricardo, your audio video is frozen.
Yeah. Sorry, Ricardo. I was not able to listen to your question because, you were cut for an instant.
Okay, no, I just want to let you say something about the energy versus
Energy and
power.
Right.
What is the trends to attend everything? Okay.
Right. So I understand the question, and this is the main research topic that where we have energy storage, and this is the lithium-ion battery pouch cells we've been developing that you have seen here at our lab, we don't have the delivery of power. And this is where we have been focusing on supercapacitor as an hybrid system, where we can deliver power at certain moments when more power is required, but we don't want to use the supercapacitor as a storage device, right? So the idea would be to have a supercapacitor linked to the energy storage of the lithium-ion battery, so that when more power is required, we activate the supercapacitor to deliver power, and then it has been presented before once again by Unicamp. We can recharge very quickly the supercapacitor when the car is not in need of so much power for a time, right? So the idea would be to have an hybrid system where we can deliver the best of all technologies. So the best of storage with lithium-ion batteries, the best of power with supercapacitor. And once again, we are very concerned by sustainability. And that's the reason why we want to use directly ethanol in order to produce electricity through hydrogen by internal reformation of the ethanol. So that's the overall strategy we want to develop. This is research, but as I've said before, we are into applied research. So we want to make this happen inside of real vehicles so that this can be, as soon as possible, a commercial, useful solution for society. And thank you again for having me today.
Very good. I wanted to highlight some comments, okay? Ingrid already said something about the lithium sulfur technology, okay? I think from this event, a lot of conversation will multiply, okay? So going back to you, John, you will have time. Now it's totally, we say, urban land. That you say about the thermal efficiency on sodium, or 50C is a new level to easy reach or something. Can you talk about it? Maybe Philip can comment also.
Yeah, I have replied to the gentleman that sent the message directly, but to be clear, there are a number of products. Ultra high power and ultra safe are completely different. The ultra high power starts at 50C and can go to 100C. It's a very high powered cell for high power and very quick discharge of its energy. The ultra safe, there is some confusion in the market when we mention sodium. People confuse it with sulfur, and also liquid sulfur runs at a very high temperature. Sodium ion is very wide in its ambient temperature capability. So it operates at between -20 and +60 degrees. So first of all, in some of the markets that I described earlier, such as the Indian markets and Asian markets, where ambient temperatures can reach 45 degrees quite often, it's very well placed for those markets. Whereas the traditionalists will recognize that lithium ion doesn't like operating in those hot temperatures, and therefore by default you have to increase the amount of cooling that you bring into your packs and your modules. So sodium ion may not necessarily have the energy density of lithium ion, but it has benefits in terms of heat capability, and also the fact that it is completely designed for a different market, a low-speed electric vehicle market. If you wish to go, if you also want to go onto our website at emptypower.com, there's a full range of specification sheets as well, which maybe will explain the different products in a better way. There was also a question about our ultra energy cell and its capability of operating at 3C. Was this similar to the Tesla cell 21700? And the answer is I'm not sure of the Tesla cell specification off the top of my head, but it is a comparable cell to the energy, I think, is the description.
Okay, John, I have some difficulty to listen you at the end, but I got all the information. Any other comments, Felipe, you want to complement and just to finish this panel?
Thank you again for having me. What is the most important for me to say right now is that we can develop together the solutions of the future. In order to do so, we have to collaborate. So we are very open here to collaborate with all your research center, all the companies that have presented today their solutions. So I have let my data on the slides, and you will have the slides. I'll be more than happy to hear from you later and develop projects together. Thank you so much for having me.
Yeah.
Okay, I would like to thank you both for the excellent presentation contribution. I apologize due to the short time, okay, but the first time, okay, I saw a lot of possibilities in the future, and I think it's just a start for all the cooperation, all the conversation, and me starting together all the project, all the mobility future for the world, not only for Brazil and the UK, but for the world. Okay, congratulations. Thank you very much. Okay.
Thank you very much.
Thank you.
Thank you.
Okay, so far for the last panel, I would like to invite Mr. James Hockley. I apologize if I pronounced something wrong. He is the Senior Commercial Manager at the Williams Advanced Engineering, and with this presentation, Specialized Battery System, Cross-Sector Operational, Adopting Future Technology. Welcome, Mr. Hockley. Now I am already seeing your presentation, so it's your time.
Yeah, so yeah, good afternoon. Thanks very much. And you pronounced my surname perfectly. Thank you for that. Many of my fellow countrymen struggle to pronounce it correctly, so thank you. So I wanted to start just by giving an introduction to Williams Advanced Engineering, just to give an idea of who we are and where we operate. So we are the engineering and technology services business, which is from the Williams Formula One team. So we're actually based on the same campus in Grove in the UK. So we're about 20 minutes by car from Oxford. And we were formed in 2010, as we say, and it was really to formalise taking the technology that we've developed in Formula One, our approach, and taking it to the market. The real focus of this discussion today is around electrification, which is where we enjoy quite a strong position in our core markets. We're around 350 employees in the UK, and in addition, we have a battery manufacturing joint venture in the UK called Hyperbat, which is with Unipart, who are a global manufacturing logistics company, who are our key partner in that area to bring that manufacturing know-how. We provide engineering solutions in a variety of markets, predominantly automotive and motorsport today is where we enjoy, a reasonably large amount of business. But we also find ourselves growing our position in defence and aerospace, healthcare and emerging markets. For example, you may have seen in the press some of the mining programs we're currently working on. Just on the right-hand side of the screen there, you can see some of the kind of automotive companies that we deal with. And generally, you can kind of see a theme of premium products coming through, which is where the majority of our customers sit. To give a history of our electrified systems, so we started developing battery systems for KERS in 2009. We actually developed an electrical and mechanical solution. We also developed a flywheel, but we, as did Formula One, went forward with chemical battery storage. We then started to grow our technical services offering, and we delivered F1 derived technology into the CX-75 road car for Jaguar in 2011. And that vehicle sort of, whilst it never went to production, enjoyed some fame in the James Bond film Spectre as the villain's car. We continued to develop our position in this market, and actually in 2014 we were selected as the battery supplier for Formula E, and it's a one battery series, and it still is today. So for the first 4 seasons we were supplying the batteries to all the teams on the grid. Alongside these projects we're able to talk around, we delivered multiple demonstrator vehicles for OEMs who were looking to prove that electric cars didn't have to be boring, such as the Nissan Blade Glider you can see there in the screen. And as we sort of went on this journey of engineering services and solving prototype kind of first of a kind challenges for our customers, we began to initiate more serious and detailed electrification projects looking towards series production. I mentioned that we have a joint venture with Unipart called Hyperbat, which gives us a position in supplying battery systems in volumes for lower volume programs. We also have committed to moving away from our motorsport battery management systems towards more high volume focused, lower cost battery management strategic control mechanisms. In addition, recently we've delivered record power density for Lotus Evija as a technical partner on that program, and we are currently the sole battery supplier for ETCR, LMDH, and the next gen Formula E batteries. So just to give some examples of the programs we're able to talk around, you can see that we deliver many programs on 4 wheels, but also we have deployed battery systems in the marine sector. We've delivered batteries using sort of quasi semi-solid state into a pseudo satellite application, and also working with customers such as Anglo American on large ultra class mining trucks. That's actually a fuel cell EV. So it's been interesting to hear about some of the fuel cell discussions this afternoon. Coming back to what Williams Advanced Engineering do with their partners around battery systems, it really falls into 4 key pillars. So they are cell technology, and we've heard about a lot of that today already. And I'll apologise in advance. I'm going to talk about it a little bit more, but I'm also going to go into Pac Integration, advanced BMS systems, and also multi-chem. Many of our partners are unable to easily draw benefit from the significant industrial inertia delivered by electrification. And actually the technical solutions do not address their specific challenges. And so these pillars actually in some way do help to guide our partners through that. So looking at cell technology, it leverages our know-how, capabilities and facilities, as well as our established relationships. And we have a network of many cell manufacturers and technologies, and with varying TRL levels and unique propositions. So we're talking with people that are the established automotive supply level already, through to niche or emerging technologies or players. We've delivered programs using state-of-the-art lithium-ion cells in varying formats, so cylindrical, pouch, and prismatic. We've also looked at systems and delivered systems using lithium titanate, lithium sulfur. We've done some demo packs with sodium ion, and as I mentioned, lithium metal. We're also in advanced trials with some fully solid state technology as well. I think, as mentioned at the beginning, this large network also enables us to help find the right solution and at the right price. And as we're finding now, critically with the capacity to support the program. And the purpose of that image on the right-hand side is to highlight that, many of the cells that we access, sometimes you can get locked out of them because of the sort of macro economy of very large OEMs controlling the supply. So, Tesla have a very famous type with Panasonic, for example. So it's making sure that we do not design in what we would call unobtainium or things that simply the customer won't be able to get. I'd say that we're recognised as leaders in thermal modelling of cells as well. Within complex systems, making use of advanced intercell and electrochemical modelling techniques. And a value of what you see on the screen here is that we're able to apply our techniques to the exact usage case of an application. And the benefit of that is really twofold to our partners. So on the first part is that our partners have confidence that the product will meet the requirements that have been set. But also it gives us a sufficient collection of credible data that we can then use in partnership with cell manufacturers to manage the commercial warranty requirements that come on these programs. As is often the case, the data sheet will not necessarily be indicative of how the cell is going to be used in the field. So it's really important to connect those things together and make sure all of the stakeholders commercially are comfortable with what's going to happen and that everybody's protected through the supply chain. So coming into Pac Integration, I mentioned that optimizing cell to pack efficiency is critical. Many of the mainstream automotive EV platforms that you see here are looking at using a flat optimized floor pack. So we've actually developed something similar ourselves in the FWEVX platform. But ultimately, utilizing the market position that the likes of Porsche, Audi, Jaguar have, they're able to develop a slightly customized chemistry, a bespoke cell format or module format, which delivers a relatively simple battery system to integrate, build and test. Now, for some of our partners, that's not really a viable option for various reasons. They need a product that not only competes with some of these products that I'm showing you on the screen, but also outperforms them and justifies that premium. So just to give you some examples of the challenge that our customers face. So if we look at the Aston Martin Rapide, for example, the mission was ultimately converting an existing ICE vehicle, and therefore it required a battery system which delivered the right performance, but also it was structural performance that was critical to avoid rehomologating the whole vehicle again. So we had to design a system that behaved in the same way in dynamic situations, but also in the case of a crash situation, all of the crumple zones are unaffected and the vehicle behaved the same. You can just see here by looking things like the LMDH program, whereby they're just looking for significant power, which is actually the same case in the Formula E Gen 3 application that we're currently developing. So on top of the less generous geometry, it's a high power requirement which simply cannot be delivered by those high volume cells, which many of the car makers have already invested heavily into to get the costs down. Extreme, again, is a great example of designing for operations in massively inhospitable environments. So this system is dealing with extremes of hot, cold and humidity, all of which several of the other presenters have all described as not preferable for lithium-ion cells. So again, we've had to look around, how do we manage that and also accommodate the vehicle package, because the chassis is needing to provide significant robustness for that off-road application. So just a few examples there of kind of how we have to help our customers solve different problems to the mainstream. I think also simulation-driven design is critical to making the development program work commercially. So I mentioned on the one hand, some of our partners may not be able to finance a customized cell. Similarly, it might not be viable to develop 100 prototype batteries to do various mechanical tests. Rather, use and leverage simulation design to speed up the position in the marketplace. And we deploy CFD extensively to study that thermal behavior of cells in battery packs with steady or transient drive cycles. So it could be a track lap or fast charging. And this includes use of advanced electrochemical models and the modeling that I showed earlier, looking at the jelly roll, can tabs, mandrel, etc., to enable accurate prediction of the electric parameters of each cell, look at any coolant pressure drops and how we might be able to manage them, and also mass flow distribution across the pack. I think thermal runaway is the other side of this. That's another very important test to give confidence that you can isolate the worst case scenario. And we have good experience of looking at different thermal runaway simulations, not only with kind of fundamental base cooled systems, but also in immersive cooled systems. Very often we work with partner organisations to conduct the real world testing in order to validate these simulations and achieve the necessary global certification. As mentioned, we have experience designing modules using a range of technologies and cell formats, and for a number of applications, and a few of the modules we developed are actually on screen here. And ultimately, this enables us to rapidly design and test a new module to battery concept. And also, we actually have experience of working with cell manufacturers to maximize the cell performance through the mechanical housing and the control systems that we put around those cells. Moving on to the third pillar, which is battery management. This is an established technology area for WAE, and our technology roadmap features continuous R&D investment into BMS technology. And as I mentioned at the beginning, our systems actually trace their roots back to the 2009 Williams F1 powertrain for KERS, which we developed entirely in-house, hardware and software. Our approach is to have extremely high power processing capability, as well as developing a platform that's able to be delivered with ISO 26262 and ASIL C or D capability. We take a generally holistic approach to control systems, delivering improved performance for the critical themes as we can see here on the screen. And the way we do that is to have a slightly more interactive algorithm approach. So traditionally, you would estimate these states individually using open loop outputs. And what often can happen is that the algorithms effectively fight one another and therefore deliver inconsistent calculations. So our approach couples the algorithms and delivers a one voice most likely solution, which in turn improves our state health estimation and allows us to open the performance parameters. So we're able to improve fast charging and power capability. And also that enables us to deliver sort of more intelligent diagnostics and fault prognosis data to our partners. We then bring that all together into the fourth pillar, which is looking at multichem. And we've talked about this hybrid system a few times today. And for us, it's bringing those trade-offs together and looks to manage them in a different way. And so the way that we look at this is we leverage the cost-efficient mainstream cell technology and we couple it with the right amount of optimum, generally higher value power performance. And in doing that, we're overcoming the inconsistent power availability that our customers may suffer from in their drive cycles. We're also managing the energy and power compromise, so that pursuit of range, compromising performance, sort of triangle that we've been discussing. But also we can use the benefits of some of those novel high energy cell chemistries on the other side by bringing that power density to manage the really large sort of peaks in the drive cycle. So we are demonstrating that this will provide scalability across a number of different vehicles, and we see this in motorsport through to heavy duty ultra class trucks. But ultimately, that's our four pillars. So sort of the conclusion of how we are bringing these technologies together is at a headline level, we're able to, in some applications, increase usable energy at the target power density. We're able to increase the thermal efficiency of any system because we are bringing in those high power capable cells, for example, to reduce the power draw. That also means that we can reduce the number of cells in some systems because we don't need to scale the pack up as high to get to the power and energy requirement. And using those more advanced calculations, analysis, and control systems tools, we're able to effectively reduce the hotspots in the system and optimize the battery health to diagnose a fault before it becomes a significant issue. So that's really the main messages for us today, and I'd be happy to take any questions once we've heard from the next presenter. So thank you.
Thank you very much, Jen. Now we will have the invite to Mr. Tijan Orcaio, team head of the JBS Europe, talk about the hybrid competition in Brazil. Welcome, Jen. We're seeing your screen, so go ahead, introduce yourself. Thank you.
Okay, so first of all, thank you for the invitation. Today I will talk a little bit about the WDRC, so the tech hub that we are creating here in South America. Basically, the WDRC, it's a bunch of different development areas that we are creating. So we are starting our company here, keeping the focus on the creation of the first hybrid vehicle based on the World Endurance Championship regulations. So we are being the first one develop this kind of vehicles in South America. So the main focus on the development of this vehicle is to keep the international regulation in terms of safety, and mainly because of the implementation of new technology. So we are, of course, developing the vehicle, but more than just a vehicle, we are creating a new business model for the motorsports that will really change the way that we know the motorsports nowadays. And afterward, I will present a little bit about our vision and how we are moving now. Of course, I cannot go into too much details, mainly because of the disruption that we will cause in this scenario. But I can, of course, say a little bit about, and I will be open to discuss if any company is interested, because our vision is not just to create and develop a new hybrid vehicle in South America that have never been done before, but we are creating our race series here to create a technology, a new platform to foster research and develop new technologies for all the big tech companies, the telecommunication companies, the automotive companies. So our intention is not to just design the first hybrid vehicle in South America. We are seeing further than this, right? So first of all, I will present a bit about the vehicle that is where we started our company. So basically, here's the shape of the vehicle. So it looks like a Le Mans prototype, mainly because we are following the LMG regulations, right? So as I said before, it was never done before in South America. So we are being the first one. And well, we are growing faster. So we have currently some companies already together with us. One of those is one big tech company that is providing HPC, so a high performance computer to the team that is allowing us to develop really fast the aerodynamics, all the transient simulations that we need to do. And of course, they are not working together with us just because of the vehicle. The vehicle, it's important. The race series is important, but we do have a bunch of different vehicles, like James just presented. We do have Formula E, Extreme E, Formula One. So we do have a bunch of race series in the world. And as I said, we are not interested to be just one more race series. We are interested to be a new race series with a different purpose. So I will just comment now about the name of the company and the race series itself, that is WDRC. that the meaning is World Development Race Championship. So our intention here is to develop new technologies for all different segments that will bring benefits to the society, right? So it's not just the vehicle itself, but for now, just keeping the eyes on the vehicle. What we are considering for this vehicle, so we are considering at this moment a hybrid parallel architecture, where we do have an internal combustion engine in the rear axle here that it's independent from the front axle. And in the front axle, we do have a electric motor that it's capable to store the energy while we are braking. So the energy flows through the engine, through the converter, and it is stored in our energy storage system. And while accelerating the vehicle, the front axle help us to accelerate the vehicle. So all the energy stored in the energy storage system goes in the opposite way, so pass through the inverter to the engine motor and help us to do the acceleration. So this is just to give you an idea about the system that we are considering on this vehicle. Of course, this architecture was used by us with the intention to have different opportunities to develop here in our vehicle. So as I said, our vehicle is not just one vehicle, so it's a development platform, right? So we are totally open to change it if some company have some interest, so to apply something different here. So just going a little bit further on the electric system that currently we are developing. So it's basically well, the engine itself, it's a commercial engine that have a 200 kilowatts peak power, and if there is some company interested to plug your own electric motor on our system, on our vehicle, and is interested to develop new electric motors, we are open to change it. So nowadays we don't have any kind of sponsorship on the electric motor side. So we are totally open. And also for the battery pack here, so the storage system that, as we already heard some of the panelists here talking about the batteries and the super cap, and our choice was to go to the super cap due to the two reasons. Of course, we know that we already have batteries with high technology and capable to deliver us really high energy in a short amount of time, like John just presented from Williams Advanced Engineer. But mainly because we are starting this company, and I think that the biggest companies from battery are keeping the focus and the eyes on the big OEMs. So sometimes it's difficult for us to get in contact with the companies that have this technology. So that was the reason that we decided to develop our own super cap storage system. So basically the super cap, it has a 660 voltage. And well, just to give you an idea what the amount of energy that we are talking here, just in the braking of the end of the straight, like in Interlagos track here, we are capable to recharge about 20 cell phones, right, in just 3 seconds. So it's really a huge amount of energy. And that was the reason that we decided to go to the super cap. But again, we are creating not just a vehicle itself, we are creating something different than every other race series that you have seen before. And we are moving faster here. So we started this project just about 1 year ago, and our idea is to not create just a car, but the car will be the vector for us. So it will be the place that we'll put as much technology as we can. So we know that in the future, the vehicle will be like a big cell phone with a lot of technologies on board. And of course, in this panel, we are discussing about the battery technology, but we know that the vehicle will not be just the battery. The battery will be really important, and that's the reason that we are discussing here. But the vehicle itself will have a connectivity, we will have the electrification and a lot of other stuff. So for us, the vehicle is just the way that we will develop new technologies. And of course, for the battery, it's possible to test different concepts in this vehicle. So our focus in do the first vehicle in South America to be the first vehicle hybrid development here in South America, because everybody can look for other vehicles to do it, but we are moving directly to create the new race series, because our intention here is to have a real proving ground where we'll be able to provide information for all of our partners about the parts that we are testing. So imagine that we have here in the grid every single vehicle reporting to the race series that is unique. So if you look for other race series, you will not find any kind of race series that work in this way. So we have usually different teams trying to do your own development here. And our intention it's not to do it. So we will have like 20 vehicles or 30 vehicles capable to do different tests. So let's say that your company is interested to test the solid state battery with different components. I mean the component A, component B, component C, and we can put it on these vehicles. So let's say in 10 vehicles we can put the battery A, and another 10 vehicles battery B, and battery C, and we'll be able to acquire the data in real time and provide this information for our partners. So in this way, it's the unique way that we can really speed up the development time, because currently, if we're thinking about in some OEM trying to develop something in-house, they have just a few vehicles and really cost involved. And here we are doing the testing in the event, right? So we have other ways to get money to invest in the development of new technology. So basically, we are creating the tech hub here. So that's the reason that we are calling the tech hub. The WDRC is the name of the series, but the tech hub is where we will develop all the technologies. And as I said before, our intention is not to keep the focus on the vehicle itself, but every new technology that will bring advantages for the society here. And but for this moment, just keeping the eyes in the automotive industry, the technology companies and telecom. We are creating inviting. Okay, someone is telling something. Okay, no, so go ahead. So we are creating an environment here where we are trying to put all the key stakeholders, so the industry, the universe, and the motorsports in working together in a collaborative environment. And with one huge advantage here from South America, why it's growing here in South America, mainly in Brazil, because we do have some incentives from the government here that invest a huge amount of money to develop new technologies. So we have basically 3 different laws that we will take advantage here. One is a focus is used for the sports in Brazil. So they invest money to incentivize the sport here. The other one is more focused on the development of new technologies. So we will be able to take these government incentives as well. because we will develop new technology here together with the company that is interesting. And there is another one that is directed to the automotive sector that we will have as well. So basically, we are able to get all the government incentives here, and we will be able to use these incentives to invest in the development of new technologies together with the companies that are interested to do it. And there is another advantage here that it's really important to the companies is that currently the Brazilian development cost, the engineering cost, is really low. So recently we had a big OEM that just stopped to manufacture vehicles here, but they just kept the development center here mainly because of two reasons. The engineering cost is too low, and the quality of the Brazilian engineers, the knowledge of the Brazilian engineers it's high compared to the other center of development. So if we had a look on the European side, the North America, Australia, and China, India, currently the Brazilian development, the cost is really low. So we'll be able to develop together with the companies in a really low price in the next years. So basically, currently we are just assessing the marketing for potential partners. So the idea here is first step is to look for companies that can work together with us and they are interested in developing new components and new technologies. Because as I said, our intention here is not to create new technology, to sell the technology. So our intention is to develop technology together with the companies that are working with us. A second level is the sponsorship way. So it's a marketing way where the companies that sponsor us will be able to get we'll exploit the future brand and technologies that we will develop in these race shears. And the third step, that there is different companies that have startup programs that also will invest in the company, but also will take advantage of the results that we will bring, because as I said, we are creating something unique here. And unfortunately, I cannot give more details because we don't have here an NDA, and it will be open to everybody. But for sure, we are totally willing to discuss with the companies that are interested to work together with us in this new environment that we are creating, this new disruptive method that we are creating for speed up the development and develop new technology. And the latest, but not least, is the usage of the Brazilian government laws that I mentioned before. So there are companies that have a development center here in South America that can take the advantage of these laws if they go together with us. So just to finish here, so this is our slogan. So as I said, we are working today while we are investing for the future, because we are creating something really new, but we are keeping our eyes in the future. So how we can improve the development efficient for the companies, how we can create new technologies for the society, and basically this is the vision. So I just left here in the right side my email for the companies that are interested to discuss a little bit further and know what we are doing. So I would like to thank you again for SAE for this time.
Okay, Jan, thank you very much. Now we will have the last Q&A session. I would like to ask Jean and Hoxie to open your camera and microphone, and feel free to send questions on the chat. We will choose one to be answered live. Okay. I would like to highlight one question from Adriano. I was talking with him as a volunteer, also as myself, for the Formula Psi Electric. I just learned yesterday there is going to have also a hybrid competition for Rally dos Sertões. Yeah, very good news. Okay, So
Okay.
he's working at my neighbor, okay, in Cotia. Okay. He has a question to James. Okay, James, what are the main challenges of immersive liquid cooling compared to base plate cooling system? Could track a little bit more about the cooling system of the multi-chain models? Does it have a common cooling solution? Could you please help Adriano? James, your microphone is still.
Yeah, I'm still.
Okay. Now you're.
Sorry, I had a classic COVID problem of being on mute. So, yeah. So to answer the immersive versus base plate cooling question first, so there's a couple of things. One of them, as a sort of negative for immersive, is it can drive more expensive component costs at a vehicle level. So typically, you're going to need probably a more aggressive or powerful pump to manage the different viscosity levels of the fluid being circulated round. It can also deliver a disadvantage for mass as well, because you're putting more liquid into the system, whereas maybe traditionally there would be air, so there's a disadvantage, which therefore base cooling picks up those as benefits. But the main benefits of immersive are typically you're able to evacuate more heat from the system and move it round more quickly. And actually you can get a better volumetric efficiency of cell packaging. So in some scenarios, you're able to move the tolerance closer together for the cells because you have a better cooling medium. So that's probably the main kind of challenges, benefits between the two. Now, with the multi-chem module, the cooling system's agnostic. Typically, when we've deployed it so far, it's been with base cooling, but again, it's a control mechanism above the module. So it's an agnostic decision depending on the application. Typically, you probably wouldn't want immersive because the benefit of having that high power capability in a smaller box means you're not having to push the whole system as hard. So that's part of taking that complexity away.
Thank you. Again, there's two questions, one regarding the LCA and another for the worries to, at the end of the competition, what's going to happen with the batteries? Can you explain this question?
Yeah, I can comment on that. So I think you're right, the sort of life cycle analysis is a really important point. And we have looked at that in terms of the sort of 3 R's, in terms of reuse, remanufacture, and refurbish. So in many of the OEM programs that we look at today, we actually tend to contract an external expert in the UK who has expertise in actually doing things like refurbishing gearboxes. And so part of their journey towards zero emissions is to look at how we can take that battery pack assembly back down to its most useful parts, whether it's modules, cells, sub-packs, whatever it is, and find a secondary application. So whether that's kind of stationary energy storage or even I suppose things like you hear about now, how are you going to recover electric vehicles when they run out of battery by the side of the road? Like some people today drive until their petrol's empty and they lose power, same problem. So there's a variety of markets which may, in the longer term, attract second life batteries. And there is a glide path that says they will become lower cost in the future as there's more supply available. And equally, it's around designing the system itself to be serviceable to an extent that you don't have to put the whole battery in the bin when there's one bad cell. So there's the kind of design answer, and there's also the agnostic creating a market for the batteries when they come to the end of their useful life in a vehicle. So for sure, most of our automotive customers are asking about how we're going to manage the carbon footprint of the system over life. And it's a really important topic.
Okay, thank you, James. Jean Caio, Just to finish, okay? Yeah, could you reinforce what do you see all day on the event? How we can help JDS
Yeah.
to put this challenge on place?
Yeah, currently, as I mentioned, we are looking for big companies with a good future view that is interested to go on this path that we are creating. So as I said, I know that for some big companies it's difficult to see in this disruptive environment, but as I said, I can guarantee that we are creating something that will disrupt the motorsports, the way that we develop new technology in the next few years. So we are moving really faster, and I think that the best way for us is to have the UK companies or Brazilian companies that are interested to move in the development of new technologies. In this panel, we are talking mainly on the battery side, but even if there is people in the audience that are from other companies, from technology companies that are interested to move together with us. And I just left my email, and as I said, we can sign an NDA, and for sure I can present all the roadmap that we are working together with the big company, the big tech company that I said before that is working together with you. We are talking with the tidy development teams as well. So we are really spreading our actuation area. So I think that all companies from these segments initially, so the big technology companies, the telecommunication companies, and the automotive companies can just contact us, and even the universities from UK, universities from Brazil, because as I presented before, the intention is to connect all these key stakeholders, right? So I think everybody is welcome to participate together with us at this moment, of course with the proper documentation to guarantee that we will move together for this new future that we are creating today.
Okay, yeah, okay. Such a small company like Williams in advanced engineering, something like that.
Yeah. I think that Williams, by the way, can get a really huge advantage because, as I said here, we are creating one of the key points here is, of course, we are not just creating one more race series. As I said before, we will have like 20 or 30 vehicles to really test. So, as I said, we can put the new batteries that Williams is developing in the 10 vehicles and different variables in the other 10 vehicles, and we'll be able to do it because, as I said, we will not have small teams trying to survive. We will have 20 or 30 vehicles really working in order to develop new technology. So for sure, for Williams, it would be nice as well. We can really speed up the development from Williams and any other company that get interested on do this kind of agreement with us, right?
Okay, that's a provocation. Okay, James.
No,
The main goal of this event. Okay, go ahead. The main goal of this event is to put the brilliant minds to know each other and to start a conversation. That's the final ending that I want to close this session. Okay, I would like to put my words right now. I want to thank you, the SCA Brazilian staff, from Ivan, that's support on this session, Vanessa Viana, Valeria Lima, Thais Bozo, Thais Costa, Ronaldo Bianchini, Erwin Franiak, Camilo Adas, okay? And also the entire staff from the Electrical Hybrid Vehicles Technical Committee. Special thanks to Maria de Fatima, Raul, Adalei, everything that's going to help to this to happen. Of course, I cannot forget once more. I would like to thank the event's exclusive sponsor, the British government in Brazil and the UK Departments for International Trade, BIT, Beatriz Ozaki, Karim, Negley. Ron, if you want to talk about something, please just open the microphone. Okay. So this is, I think the goal was reached. I was very excited about all information I learned today. I hope to see you again in special meetings. Okay, so I'm asking you to follow the SA Brazil social media or access sabrazil.org.br for more information about the next event. Thank you and have a great day. Thank you to everybody for the excellent contribution, and I see to see you soon. Okay, thank you. Bye bye.
Thank you.
Bye bye. Thank you for all.